Hello. Today we have a practical lesson on the relativity of mechanical motion. Let's start solving. A passenger is walking from one side of a ferry to the other as it approaches the pier. If the passenger's velocity is 1.5 tenths of a meter per second north of the ferry, and 4.5 tenths of a meter per second at an angle of 30 degrees west of north relative to the water, then what are the directions and magnitude of the ferry's velocity relative to the water? Let's first write down the conditions of the problem and look at the figure to see what the construction of this motion looks like. We want to find the velocity of the ferry, so we will denote this velocity by the letter v1. And we will denote the direction by some angle of theta, which we will look for further in the problem. We know the velocity of the passenger relative to the ferry. Let's denote it as v0. And it's 1.5 tenths of a meter per second. And it's pointing north. And it is also known that the given passenger moves with the speed v2 4.5 tenths of meters per second, but already in the direction to the west at the angle of 30 degrees. This angle we denote by the letter alpha. We have specified all the data, put the question. Now let's see how it will look in the figure. So we will take the direction to the north in this direction. This direction is the north, and this passenger moves along this direction with speed v0. We also know that the speed of this passenger relative to the water is 4.5 meters per second and is directed at an angle of 30 degrees to the direction to the north and in the direction of northwest. And that velocity is then directed at an alpha angle like this. That's velocity v2. Now what can we say about the velocity of the ferry? We can say unambiguously that the velocity v2, i.e. the velocity of the passenger relative to the water, appeared due to two motions. It is the proper velocity of both the motion of the passenger relative to the ferry and the motion of the ferry relative to the water. According to the law of addition of velocities, we can say that the velocity of the passenger relative to the water, v2, must be determined by the sum of two velocities. These are the velocity of the passenger itself, v0, and the velocity of the ferry, v1. To follow this rule, we can look at this figure, build it up to a triangle, because it is by this rule that the two vectors, v0 and v1, will add up. And here we can see that if we add vector v0 to vector v1 so that the resulting figure will form a triangle, then we just need to connect the end of vector v0 to vector v1. Connect the end of vector v0 and the end of vector v2. And we get the direction of travel of the ferry. Also somewhere to the northwest, but the angle we see here is different. That's exactly the angle we're going to determine. And the first question, probably we will put the value of velocity v1, how to find it based on this construction. We have received, as a result of construction, a triangle with known sides v2 and v0. There is an angle between them, and it is necessary to find an unknown side in this triangle. I remind you that such cases, when we get an arbitrary triangle, i.e. non-rectangular, it is convenient to solve through the sine or cosine theorem. Depending on the situation, you can use either one or the other theorem. Here the cosine theorem fits very well because we know the two sides, and the angle between them. We need to find the third side of the triangle. Then let's write down the cosine theorem for the unknown velocity v1. v1 is equal to the square root of the sum of the squares of the known sides minus their doubled product by the cosine of the angle between them. All that remains is to substitute the value and calculate the speed of the ferry. v0 is 1.5 tenths, v2 4.5 minus their doubled product. And the cosine of 30 degrees, let's take it as 0.87. And after calculations, we get an approximate answer of 3.2 of a meter per second. So, we have solved half of the problem, that is, we have found the speed of the ferry. Now the question is in what direction the ferry is moving. We use the method of decomposing the velocity into its components. And for simplicity, we will take the direction to the north is the y component. This way we put a point and the direction to the west is the x direction. The velocity v1 itself is placed here like this. This is velocity v1. And now if we plot the components of this velocity, we get v1i, it's facing north, and v1x, it's facing west. The angle in this case is formed by two velocities, v1 and v1y. How to find this angle? But given that we already know v1 in this triangle, that is the hypotenuse. It is clear that it will be convenient if we find one of the cathetes. In this case, it is more convenient to find this component along the x-axis while let's look at the figure. We see that along the y-axis, i.e., along the north direction, we have several velocities, i.e. this v0 has its own component along this direction. Along this direction. Along this direction we have components v2, i.e. if we plot it, and accordingly we get the total component v1y based on these two components. But this is not very convenient because there are too many components working here. But if we look at the x component, we get here only one component of the vector v2. I pay attention to this perpendicular that we missed, and it is also a component for the velocity v1 along the x-axis, so we can write that v1x is equal to the component v2x, because we don't have any other vector components along this direction. So our problem is to find the components of the vector v2 in this direction, and then write down the necessary trigonometric relation to calculate this angle θ. Then we understand that the angle θ will be found based on the knowledge of the hypotenuse in this triangle and the opposing catheters. These are the components just along the x-axis, and this connection allows us to make the sin of the angle θ. Write down this ratio, i.e. v1x component as the opposing catheters, and divide by the velocity v1 itself. Or instead of v1x, we substitute v2x, and they are equal to each other. What is v2x? Let's look at the figure. In this case, v2x is the velocity component v2. It can be easily found if we adjust the alpha angle in this triangle here, and see that this is the opposite cathetus for this alpha angle in the velocity triangle with hypotenuse v2. Then it turns out that v2x will be equal to v2 times the sine of alpha, and divide that by v1. All we have got the final formula in which we know v2, the velocity of the person relative to the water angle alpha, we also know, and v1 we have found from the previous condition of the problem. It remains only to put the value and calculate. And so the sine of theta angle is 4.5 times. The sine of alpha is the sine of 30 degrees. 0.5 times the tenth and divide by 3.2 tenths. 2 tenths, and we get a value of 0.70. If we look at the Bradas table or calculate the sine value for theta angle and get the value of 0.7, we get it for theta angle, which is 45 degrees. That is, in this case, the ferry moves at an angle of 45 degrees to the north and at the same time with a responsible angle of 45 degrees to the west. So it's a northwest direction. All in this way, we have solved a problem in which the law of addition of velocity is already taken into account, taking into account the work with vectors. Such problems help to understand more fully the subject of relativity of mechanical motion. I'll see you in the next lessons. Goodbye.